Good morning and welcome to our second session on this last topic of area, well, really sort of perimeter, area, and volume. Let me just check if everything is working as it should. It's a little bit skeptical. Okay, so far so good. So let's remember what we did last time. We started by looking at perimeter, which you can't make super complicated. You need to know the... Can't see the screen again? This is why there's no way for me to check that. Okay, let me do this again. Okay, how about now? It makes no sense. I'm doing exactly the same thing. One time it's happy, other time it's not. Because why not? Why not? Okay, good. We'll have to check well, we have one more lecture tomorrow, so we'll have to check at the start of tomorrow as well. It is tired. It's getting tired of this. Yeah, you're right. Okay, let me start again. Okay, let's remember where we were. We started with perimeter. Can't make it very complicated. We just need to calculate somehow all the line segments, all the edges, and then add them up. We did remember uh, that, well, not there. Where was our circle? Doesn't matter. We remember that for the circle, it's called the circumference, and we already know that, 2 pi r. Then we looked at a little step forward, just a little teeny tiny step, and already the area formula in general for regular polygons look a little bit more intimidating. It looks a little bit more intimidating. We got an idea of where a formula like this could come from. That does come from in this case. You decide if that's too much for you or not. But in terms of testing, we need to just be able to use the formula, understand the pieces in it, and then perform the calculation on whatever calculator you have. Perform that calculation correctly. Right. So that's where we were. What was this? We just practiced the formula a little bit. Now we are moving on. Well, we're sort of moving on. Not really. We're still on the topic of area. I just want to include the circle in this discussion. Now, many of you, if not all of you, know the formula already for the area of a circle. And let's draw a circle here. Where's my drawing? Of course, I need the radius of the circle. Circle looks circular. And we'll specify here. There's the center. And I have the radius r. Area of a circle with radius r. We all should know the formula, but the question is, where does that formula come from? Where does it come from? It's one thing to just memorize these things. There's a lot of background noise here. I'm not sure if you're picking it up. Let me just go and close the door. I'll be right back. So to better understand where the area formula for a circle comes from, I want to look at this. So what we're going to do is try and approximate the area of a circle with something we know the area of a regular polygon. Now, in the case of a triangle, the area of the triangle isn't even close. I press the button doesn't work sometimes. In the case of a triangle inside a circle, the area of the triangle isn't even close to the area of a circle, right? But if I look at a square, then the area of the square is still not great, but it's better than the triangle. So here the error that I'm making to approximate the area of a circle by way of the square is 36%. That's there's big space I'm missing here, right? But as I look at a larger polygon, 5, you see the area, the error that I'm making by using the area of the pentagon, it's less. I'm moving in the right direction. And every time I look at a bigger polygon, my approximation gets better and better and better and better and so on. And eventually, if I keep going like this, it's going to almost be impossible to notice these gaps. They're going to get so small. Now, I can't really do that by hand, but there's always an error that I'm making. As the number of sides of the polygon, n, gets bigger and bigger, let me just see if this, as it gets bigger, 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 notice how this area, this error in the area approximation gets down and down, and it's heading towards 0, right? You can't even tell the difference anymore, and I'm only at a 41-sided polygon. I can't even notice the difference. But there is one. There's definitely an error that I'm making. It is an approximation. But as n gets bigger and bigger, they definitely approach each other. The area of the polygon approaches the area of the circle. So this is a way to approximate the area of a circle by way of looking at the area of the polygon inside. Now let's pick an easier polygon, maybe that guy. Now the size of the circle can change, right? It can be whatever. So let's pick a circle. Let's maybe, we have a circle, radius r, I don't know what it is. I want to have an idea of where the formula for the circle may come from. All right, so what we're going to do is just manage my space here. Let's see, area of circle. I'm going to use not an equal, but a squiggly equal because it's approximately equal. Let me make some space here. I might not want this line. Let's look at a polygon that I can handle. It's not going to be big. Should I try and copy the hexagon? Maybe I should try. Hexagon over here. It's not going to be very good. I'm just freehanding this, right? But it's good enough to get the idea. That last one was not good. Anything with this angle, I can't see my hand. It's often not very good. Okay, so here's my center. So I want to approximate the area of the circle by the area of the hexagon inside. Now, yes, we do have a formula, but it might not be so easy to calculate the side length, right? For the previous formula here, I need the side length. And the circle can be a lot of different size radius size circle, so I can't really rely on that. But I'm going to do something similar for sure. I'm going to look at these interior triangles again, but not in quite the same way. This is going to be an approximation. Remember, by hand, I'm drawing a very big triangle. But in reality, the triangle is going to be very small and thin. It might look like an equilateral triangle here, but in general, it's not going to be equilateral, right? It's going to have a little base, I'll call it, and then go to the center of the circle. So it'll be isosceles, but that's about it. So I want to imagine working with a much bigger sided polygon, but drawing it is not going to be so easy. So when I draw it, I want to give myself some space, but in truth, it's very small. So I'm going to have an n-sided polygon. So it's approximately the area of my n-gon, which I want to leave in general because I want to make n get bigger and bigger and bigger. So the area of the polygon is going to be n times the area of one of these interior triangles. Maybe upside down. Maybe like that, to match the one I chose. Now, I know the area of a triangle in general, whether I have these numbers or not. It's going to be a half times, I'll write it out, base times the height of the triangle. So I'm trying to derive a different thing, and the procedure here is going to be a little bit different. Here I want the classic half times base times height formula. Let me just move this. I can't tell if my talk button is always working. It's hiding behind another window. Okay, there we go. So now I want to see, well, what happens when n is not very big and I have like a hexagon. It's a little bit deceptive. But remember, I'm in reality looking at something much, much closer to the circle. I'm looking at a triangle here. I can't draw on this. It's a web page. But I'm looking at a pretty thin triangle here. Pretty thin triangle. In fact, let's maybe update it. I can't draw a polygon, but maybe I can look at a nice and thin triangle to help us visualize it. Get rid of my hexagon here. That's okay. Doesn't have to be a hexagon, right? Once it gets bigger, I struggle to draw it very well, but really now I'm only interested in a single little triangle because all these triangles are the same. So I'm going to have a little edge here maybe, and it's going to go down to the center of the Earth. That's not very good. Down to the center of the circle. I'm looking at a very thin little triangle here. And I'm going to use this as the base. And the height is going to be over here, of course. Height. So it's upside down, but the short little edge is the base. Now, I'm trying to look at what happens as n gets bigger and bigger and bigger. So it's not equal, it's an approximation, but that approximation gets better. Let's say here, approximation that we're making with this squiggly equal sign gets better as n gets bigger, to the point where I can't even tell them apart, right? We saw it here. If n gets bigger and bigger and bigger and bigger and bigger, the error that I'm making is almost negligible. It's so small. And n's only 50. I can make n hundreds and thousands conceptually. Right. Even though I can't draw that very effectively. So As n gets really, really big, the height of this triangle is going to be very close to the radius of the circle. It's never actually the radius because there's a teeny tiny gap between the circle and my base edge. But as these triangles get super thin and the base gets super short, the height is approaching the radius of the circle. So it's approximately, in the large N situation, the height approaching the radius of the circle. Radius of the circle is R. Radius is over here, wobbly radius. Okay. So it's a different kind of argument. I'm looking sort of at what they call a limit argument, as some aspect of this n, in this case, gets infinitely large. Something approaches something else. But in the meantime, it's kind of an approximation. Now I just want to shuffle some things around. I want to put my half in front. I want to put the radius over here next. And then I'm going to just focus on the n and this base length. Those together and think about that, maybe by way of the picture again. Oops. See it. So the base sits over here. Remember, it's super, super short, super small, and pretty much tracking the circle all the way around. Initially, it's not, but eventually these little pieces, they're tracking the circle all the way around. So yes, I have one of them. In the case where I have, let's say, 17-sided polygon, I have 17 of these little bases, right? I look at a single triangle, but they're all the same. As n gets bigger, I have more of them, but it'll always be, the number of them will be n. So if I then say n times this base, as n gets larger and these get smaller, they track the circle all the way around better and better. So this over here is approximately the circumference of the circle. Right? And the circumference of the circle, I have a formula for. Circumference of the circle, which I'll now put in, so I have 1/2, I have r, I have 2 pi r. That's the circumference of the circle. And if I then simplify this, I get the half and the 2 cancel each other. I have a pi, and I have 2 radius variables, pi r squared. So the area of the circle, of course, which I hope we all knew, is pi r squared. Now this argument might seem a little casual, and oh, I'm just making approximations. How could that be correct? It's correct in this extreme limit case as n gets infinitely large. It approaches the actual area. But in the meantime, like this shows, there's always an error. But as n gets larger, the error gets smaller and it's heading to 0. It'll never actually get there, but it's heading towards that. So I can look at this in what we call a sort of a limit argument to derive a formula of the shape that it's heading towards. So this hopefully gives you a taste. It's a little bit fancier, maybe, different kind of argument than our previous area formula, to at least have an idea. Why is the area of a circle pi r squared? Where does that come from? It's just made up because someone wants it to be? No, because in this argument, which we do in a little hand-wavy way. You can make it a little bit more mathematically proper. The area of the polygon, as the polygon gets bigger, approaches pi r squared. So that has to be the area of the circle. So it's something that I think is worth seeing, but of course, I'll never ask you to repeat this argument, even though you can look it up. Just having it there somewhere, having seen it once, I think has some value. So now all we want to do really is just practice this a little bit. But there's not much we can really do, right? The area of the circle is the area of the circle. But let's try and mix it up as much as we possibly can in exercise 17.4. Draw the shape stated below and calculate the circumference and the area. So I have a circle with a radius 2 centimeters, then I have a half circle, then I have a quarter circle. Can't do much more, can we? Let's just run through those just to practice the area of a circle in case you don't, for some reason, you've never seen it before or you forgot. Good either way. Position my things. Go. So, exercise 17.4. Again, we'll never show little Timmy this argument, though we could do some project sort of with easier polygons, but it's a little bit advanced. But it's good, it gives me confidence to know where this comes from, even though I might not show it in an elementary school class always. So, I have a circle with radius 2. Okay, well, I can draw a circle very easily. Let's try and make it look circular. There we go. I'll indicate the radius here, radius 2 centimeters. So the area is pi times 2 squared. So, well, I can't really calculate pi in my head now, can I? Let's do it. I'll just say 4 times pi is, and we get, let's round to 4 decimal places again, 12.5664, and it'll be square centimeters. That's simple enough. Not much we can do, right? Number 2, to a half circle with radius 3 centimeters, right? See? Now I'll cheat a little bit and draw a full circle, and then simply erase the part I do not want. Say here, that's our center. Oops, not eraser mode, center. To make a half circle, and then erase this other half that I do not see. If I freehand a circle, it's going to look all wobbly. But you have a compass and all kinds of stuff that could help you draw a circle if you need to. So you have options. I have a radius 3 centimeters over here. So then the area is going to be a half times the area of the circle, which is pi times 3 squared, because I only have half the circle. So let's calculate that. Seems simple enough. I'll have pi times, I'll just say 9 divided by 2. A lot of this is maybe just calculator practice as well. To be comfortable with your calculator, make sure it does what you want it to do. Whoops, no, I said 4 decimal places, right? So it'll be 1372. Write the units there if you want to. It's not crucial. half circle. Not much we can do. Make it more exciting. Or we can. A quarter circle. Let me draw a full circle. Then I will erase the part I don't want. Let's put the centers over here. So now I want, let's say, see, circle over there. I'll just make this bigger so I don't. I'm looking at me erasing something a little. There we go. So our radius is, oh no, the diameter. If I did have the circle all the way around, the diameter is 4 centimeters. So I'm only interested in this little guy. So the area is going to be a quarter of the area of a circle. Full circle. Full circle is pi r squared. Pi is 2 centimeters. Now this is 4, 2 squared, dividing by 4. So the answer is really just pi. Calculate it. 3.14159. So 6 if you want to round it. How do I remember that? There's a little song. You all know the song? Sine, sine, cosine, sine, 3.14159. Yeah, to help me remember the first few digits of pi. Sure, I'll sing it again. Sine, sine, cosine, sine, 3.14159. Everyone should learn that song. It's so catchy. Just want to sing it all day long. So there's not much we could do for shapes, right, with the circle. Now you could get a little bit fancier. I know you want to hear the song again, but I won't. You can maybe look at something like a window. So there's the frame of the window, and maybe it's a fancy window with a half circle on top and stuff like that, right? And you can calculate the perimeter, calculate the area of the whole thing, but it's really just breaking it up into familiar pieces. Now, I do realize that we did not calculate the circumference as they asked. Sketchy, I know. Circumference is 2 times pi times the radius, which is 2. So we can calculate that. Same. It's the same. Haha. Just randomly. I have the same answer. Oopsie. 12.5664. And that'll be in centimeters. Length measurement all the way around. The perimeter, I guess, would be a better descriptive word here of what we're looking for. As soon as I have some straight line segments, perimeter, I think, is better. But they mean the same thing, right? Circumference, perimeter, who cares? Then I have 2 pieces here. Let's break it up. I have 3 centimeters, check. I have another 3 centimeters, check. And then I have a half of the circumference of the circle, 2 pi r. Squeeze it in there. Squeeze it in and calculate it. Plus 3, not 32, plus 3, plus 3 times pi. Oh, I didn't like what I did there. Of course not. Now the half and the 2 cancel each other, so it's really just 3 times pi. So I shortened it a little bit, and we get 15.4 And the last one, we have 2, this vertical side, that's also 2, and then a quarter of the circle all the way around, 2 pi r. Radius just happens to be 2 as well. We actually don't need a calculator, but I will just show it in the chat. 2 plus 2 plus, see the 1 over 4, and there's a 4 inside the bracket, so it's just pi. Which of course will be 7 plus 3.14159. Sorry, 7.14159, so 6. 3 plus 4. Right. So not much more we can do. Like I said, we can have some interesting shapes that you do see out there, maybe consisting of rectangles and parts of a circle. You can calculate the area. You can calculate the perimeter outside. But I'm pretty sure we can handle that. I don't think we have a specific exercise. Perhaps there is a problem like that, but you can easily think of these things. Oh, what would I do here? It's just pieces that I've seen before put together. So, not a big deal. We have some time, so let's continue to surface area. Done. Almost done. I'm going to drag this out as much as I can, show you where the formulas come from and everything, just to stretch this out, but eventually we're going to reach the end and it's going to be sad. Maybe happy for you. I don't know. Surface area. So very simply, if we go back to polyhedra, the polyhedron consists of polygon faces. Let's stick to semi-regular polyhedra, where our polygon faces are regular polygons. So the surface area is just, like it says, the area of the surface, the area of all of the faces, sum of the areas of the faces. So even though I look at a three-dimensional shape, area is a two-dimensional concept. So all I have to do is know what the shapes are that act as the faces, and then calculate the area based on or using my formula for regular polygon areas. So I'm back to this guy, s squared times n over 4 tan 180 over n. So what were the question here? Let's make a new page. Fresh start. Let's see. Get some drawing practice in as well. So I have some in exercise 17.5. Size 17.5. Might not do them all. Oh, we could do them all. We have time. Why not? Number 1. What do I have to do? I want to draw the shapes and calculate the surface area. A cube. Practice. Maybe not. Maybe I just want to verify that I can draw it. It's all good. Now it's regular here, so all the side lengths are 3 all the way around, right? Surface area. Let's call it SA. Surface area. All I need to know is how many faces does the cube have? 6. Now it's a square face in this case. Don't use a fancy formula when you don't need to. The square has its own simpler formula. 3 squared. 6 times the area of a single face. What's that? 9 is 54. And that is square centimeters. Do check if the question wants you to write the units, because Be surprised. Sometimes I want to check. Do you understand that surface area is unit squared? It's an area. Even though I am looking at a three-dimensional object, we're not doing volume in this question. We'll do that tomorrow. We are asking an area question. So by testing if you know the units, there I am just verifying if you really understand what we're calculating here. Number 2, a tetrahedron with some side length. I just assumed it was centimeters. Let's just make it centimeters. They don't even tell me the units. But let's have a unit so that I can see the unit squared is my area unit. All right, tetrahedron. Now I have to practice some drawing. It's good for me. Tetrahedron's pretty straightforward. Triangle looking at me, 3 triangles at the back. And it has side length 2. Let's make it 2 centimeters. So my surface area is, well, I have 4 of these triangle faces. 4 times the area of a single triangle face. I only have side lengths. I'm not going to care about the height. I can do it with Pythagoras and stuff because it's regular. So a perpendicular line down will be a bisector of the bottom edge, blah, blah, blah. We've done that. I don't think I gain any time by doing that instead of just the formula. So I have side length squared times the number of sides of a triangle is 3 over 4 times tan of 180 degrees over number of sides is 3. I'm using this right now. You don't have to memorize it. I just don't want to jump back and forth. I only need side length and n, number of sides. And then the calculator does the rest. Now I can speed up the calculator a little bit because that's a 4 and cancels with that 4. That's pretty much it. These numbers are inside the tan function, so I can't do much there. That saves me a little bit. So let's do that. So I have 4 times 3 divided by 10. I'm in degrees. So I have to tell MathBot that. 180 divided by 3. Get 6.9282 centimeters. That does not look like a 2. So it can be a little deceptive to practice this, especially for the calculator part, because there's no way, sometimes with calculator use, there's no way to know if you've made a mistake or not. Because if I don't know how to do this, I do it in the way I think. If that's wrong, I might not know in an exam because I don't have an answer. So then if I check, well, let's calculate this and see if I get the same answer, I would just do the same thing again, not realizing that it's wrong. So it's very important in these practice questions to make sure you can use your calculator correctly because you have a target answer, so you know when you're correct. Tricky calculator use calculator often. So you want to be comfortable with your calculator so it doesn't force you to lose marks for no real reason. Number 3, octahedron with side length 1. Let's call it centimeters. 1 centimeter. Octahedron is my favorite to draw, I think. I have a little flat square as a cross section, angled, but I'm going to go with it. Then I put vertex at the top, vertex at the bottom, and connect all 4 parts of that, all 4 vertices of that cross section square with vertices, trying to have it look decent. Doesn't have to look that great. Can make that a little bit more dotted line at the back there. Doesn't really matter. Octahedron. Practice. 2 centimeter side lengths all around. It's a platonic solid, regular faces, all side lengths are the same, all edges are the same. So, not 2 centimeters, right? In this. So I have 8 of them, so the surface area will be 8 times the area of that single triangle with side length 1. So it's side length squared times number of sides of a triangle divided by 4 tan 180 degrees over number of sides of a triangle. Simplify that. 8 and 4 leaves it. 1 doesn't actually matter. So maybe that helps you. Less things to type into a calculator. Maybe. Let's do it. 2 times 3 divided by 10 in degree. 80 divided by 3. Close my bracket. That looks pretty good. Go. 3.4641 square centimeters. Enough? I guess let's do another one. Why not? I want to add one, and I think I'll have time to do that. Last one on the list in the book is a dodecahedron with side length 2.5. Let's make it centimeters again. That gives me a good chance to practice my dodecahedron drawing skills, which is not great. Let's make an upside down. That's too much. That's too much. Upside down. That. Give it a little bit of an angle, perspective, though don't really know. Then I want to draw little lines out from each one. Not gonna look great. Doesn't have to. It's okay. And then of those a little bit raised. That's how I do it. But okay, and it looks recognizable. Go right ahead. Ball like the top is a little messed up here. It fell on its side here and got an indentation. Okay, dodecahedron, side length 2.5 centimeters. Surface area is 12 times the surface area of this pentagon face. Side length squared times number of sides of a pentagon over 4 times tan of 180 over number of pentagon. I can maybe make my life simpler here. Simplify the 12 and the 4, but there's not much more to do. Let's calculator to see. 5 squared times 5 divided by 10 in degree. 180 divided by 5. Biggest one we have yet. C 129.0358 still square centimeters. It's a little more rounded, so it has more surface area. Yeah, absolutely. I want to do one. I'll add a number 5. I'll do one that doesn't have all the same faces. Let's say a hexagonal prism. Not to look like an idiot, let me just check if that's maybe already, that's already listed. See, it's like I wrote the book. I didn't see the number 5, but there is a number 5. Exactly the one I wanted to do. How convenient. So there's no need to add it or write it down. Hexagonal prism, side length 1.5. So I need to draw a little flat hexagon here. Maybe like that. Maybe not. Not. Back it up, try again. Something like that. That might be better. It's my top. There's the back. I don't care about dotted lines here. I just want to have it look decent. I can always make some lines dotted later, right? Let's make those a little bit faded later. Hexagonal prism. Why is it so low? I don't know. Side length is 1.5 centimeters. All the side lengths are the same. Semi-regular polyhedron. So surface area is surface area of my hexagons and then of the squares. So I have 2 hexagons. Hexagon, I'm going to need the formula. So 1.5 squared, side length squared, times number of sides of a hexagon over 4 tan 180 over number of sides of the hexagon. Plus, excuse me, surface area of the, well, the area of the square. I need to know how many there are. There are 6 all the way around, right? So the walls of this prism. Times, I don't need a fancy formula for that. It's a square. 1.5 squared. Get too fancy. I can maybe simplify that 2 and the 4 there. Maybe simplify the 2 and the 6 to make that a 3. Let's make my calculator life easier. Let's do it all in one go. 1.5 squared times 3 divided by 10 in degrees of 80 divided by 6. Then I have to add 6 times 1. Man, my finger keeps slipping and I type more than I want. Go. And we get 25.1913. All right, so that gives us a fair number of examples, not too bad. The only thing left to do is just note that as we did the area of polygons here, we started today by looking at the area of a circle, pi r squared, and where that comes from. You can use a similar argument, but in a three-dimensional way, to approximate or to derive the surface area of the sphere, ball, by approximating it with the surface area of the regular polyhedra inside, and then letting the number of faces increase. But that gets a little fancy. We got the idea. It's very similar to this that we did with the circle, just bigger and fancier, right? So I just made a note here that it is possible in a similar way. It uses a little bit of calculus to be more proper and precise, you can derive the surface area of a sphere with radius r to be 4 pi r squared. You see, you still have the square in the radius because I'm talking about an area, but in this case, it's 4 pi r squared. Why? Well, deriving that's a little bit more complicated. We don't really have the tools that in this course. And then our last thing to mention, to talk about next time is volume. And then we are done. So close to the end. One step at a time. Make a list of the formulas that you're comfortable using, but of course, you can look it up when you practice these questions. You don't have to memorize them right away, right? It is convenient, but don't let it happen naturally. Area of a circle, and then some applications of calculating the area, and then ended with the surface area of shapes that we are hopefully familiar with now. Are there any questions at this stage? All right, then we will end it there until next time. See you then.